Last 2 weeks, we mainly particularly focus on the construction of the algebraic geometric codes. And for this purpose, we fixed the function field of genus G. And particularly, we consider pairwise distinct places, PIs. And if we recall the definition of the algebraic geometric code, the number of the rational places will be important for the length of the algebraic geometric code, and particularly we pointed out that this number in it can be determined by the Husserl mode. So if you want to construct a linear code with longer length, you need to work with function fields which has the maximum of number of rational points, for instance, like Hermitian function fields. And on the other hand, we consider a divisor which has disjoint support, which doesn't contain any of these given rational places in its support. And we define the algebraic geometric code as an evaluation of this image of this evaluation map. So another important question: what is the structure, specific structure of the basis of a Riemann space? Indeed, it is a general, and indeed, in general, this is a difficult question for general function fields. But at least for the genus 0, we have an idea, and particularly we consider the Solomon codes by regarding these settings. And we also consider the genus 1, genus 2, and the Hermitian case. And in certain cases, we were able to describe L of G and the number of rational places, but in elliptic and hyperelliptic case, we have just estimates. But if we are able to find this n, if we are able to fix this and if we are able to compute the dimension L of G or L of G minus D, depending on the evaluation is injection or not, we are able to estimate parameters by using Riemann-Roch theorem. So this week, in this lecture, I want to turn back to genus 0 case, because now we will see that Solomon codes and the generalized Solomon codes are not the only algebraic geometric codes which are derived from rational function fields. So for this purpose, instead of considering the all rational places, we will first fix the constant field as an extension of a finite field FQ. And we will be interested in the structure in the algebraic, in the rational function field FQ of FQ to the m of z. And in this case, if we recall the construction of the Solomon codes, instead of considering the all rational places which are derived from the primitive element of FQ to the m, we particularly consider a specific, it can be also equality, specific subgroup of the multiplicative group of the constant field FQ to the m. So that means let n be a positive integer which divides q to the m minus 1 and beta be a primitive nth root of unity. So that means this subgroup is going to have order n, and for this subgroup we fix the rational places which has zeros at this given subgroup which is generated by beta. So pairwise distinct rational places. Let me notify if F1. And similarly for the transcendental Z, let me denote the zero of X and the pole of the X, pole of the Z as P0 and P infinite respectively. Pole divisor of Z. And now we consider, okay, here D is going to be some of these given indistinct places. And by using this, in the Solomon codes or generalized Solomon codes, we only consider the Riemann spaces depending on the P infinity. So that means they are the functions which has zeros at P infinity. In this case, we consider divisor which has zeros both at P0 and P infinity. And particularly, if we recall the proposition 2.3.2, in the rational function field, if the degree is the degree of the G, in this case, it's going to be A plus B, is less than or equal to n minus 2, and that we have observed that its dimension is 1 plus degree K and degree G, and its minimum distance is n minus degree G. Indeed, it's MDS. So in order to define the evaluation of L of G, the functions from the Riemann space of G at these given distinct places, first we want to understand the structure of the Riemann space of L of G. And now we will see that the functions of z to the minus a plus j's, as j runs through from 0 to a plus 1, forms the basis for L of G. And in order to see that, first let me verify in that these functions, so that means their principal divisors, is bigger than or equal to minus G. And by using the properties of the principal divisors, we can write this principal divisor as a linear combination of minus a and j. And if we write the principal divisor as p0 minus p infinity, by rearranging the last equality, for j less than or equal to a plus b, we can verify this inequality. And indeed, this shows us these functions are bigger than or equal to minus g. And we can also see that the degree, if you consider the Riemann row space L of G, since its degree is A plus B, is always positive, so that means it is bigger than or equal to 2G minus 1. By the Riemann's theorem, we know that its dimension is equal to its degree plus 1 minus genus. In this case, we get A plus B plus 1. Then, if we are able to see that these functions are also linearly independent, over base field FQ, actually it works in general, then we can claim that the total number of the linearly independent elements, the total number is A plus 1 plus B, and that these functions forms a basis for the Riemann row space. L of G. Now, if we consider evaluation map by these settings or by the notation so far, here G is the divisor determined by P0 and P infinity. And particularly by the forms of the basis of the Riemann row space of this particular divisor, and the particular form of the rational places we consider. So that means P1 will be, P1 denotes the 0 of the beta to the 0. And if you consider the definition of the residue class field, indeed, we can easily see that this first row is going to be evaluation of these functions at beta to 0. This is 1. And similarly for P2, we consider it, we define it as the 0 divisor of beta. And if you consider the evaluation of these functions at beta, we get the second row, second column as beta to the minus A, or the consequent powers of beta. And finally, if we consider the evaluation of these functions at beta to the n minus 1, we get the powers of beta to the n minus 1 from minus A to minus A plus B. And indeed, this is going to be a generator matrix of algebraic geometric code, which is defined D, let me denoted by particularly beta, and AP0 plus BP infinity. For this notation D beta, what I want to mean is the divisor we consider in this particular setting. So now, okay, we consider another specific construction of the algebraic geometric code. Just for the simplicity, or to be consistent with the notation of proposition 2.3.9 of part A, from part A, let me change of variable this minus a to L, and for A plus B, let me write it as delta minus 1, delta minus 2, with an integer which is greater or equal to 2. Then this generator matrix, if we apply this change of variables, will turn out the matrix in this form. So they are essentially the same. At the moment, it's not quite clear why we consider this change of variables, or why we want to write this generator matrix in this form, and it will be clear probably 3 weeks later. But for the moment, if you consider this generator matrix or equivalent to this one, by using these specific parameters L and delta, we can denote, actually we will see that this algebraic geometric code is also denoted by N, L, and delta with these particular choices. And indeed, this construction allows us to introduce one of the most familiar in algebraic coding theory, what is called a BCH code. Or equivalently, indeed, recall that the here dual denotes the dual of a linear code, which is determined by the inner product defined over fq to the m, because this C is a linear code over the fq to the m. And then we consider the subfield subcode of this dual code, and this is what we call BCH code. Or equivalently, if we denote this generator matrix by H, we can consider BCH code, which contains code words vectors from fq to the n that satisfies this matrix equation.